Okay, well, welcome everyone to another community meeting. This one is a special one. We are doing it in an Asian-friendly time so that we can accommodate our two speakers today. We're both in Asia, so I really appreciate them making the time to talk to us today and everybody else to show up here at this odd time for some of us. Um, so as usual, remember to put your name in the attendees list. And the agenda for today, we're going to start with some announcements as always. Then we're going to jump into the two presentations. One is going to be about sonar simulation using Gazebo Classic for the DAVE project, which is an underwater simulation platform. And then we're going to have a presentation about ignition physics, which is one of the ignition libraries that focuses on physics and has an abstraction layer for that. Then we'll go quickly over some news here that Kat curated for us. And if we have time, we can go over some topics from the community. If anyone wants to put anything here into the agenda, feel free to add. We'll get to it at the end. So let's get started. So for announcements, in case you've missed, ROSCON this year is going to be in person in Japan, and we have the call for proposals up. So be sure to submit your talks about ROS, Gazebo, all of that good stuff. And we also have diversity scholarships this year. So if you qualify, you could get like plane tickets and hotel and the conference like tickets, everything included for you to join us at ROSCON in Japan at the end of the year. I think it's October, so it's not too close to the end of the year. Another thing that's going on is that Ignition Edifice, which was our 5th major release, is going EOL at the end of the month, which is tomorrow. So we're making the final releases and just putting everything in place to archive everything related to Ignition Edifice. So you can read all about it in this link here. And tomorrow we're going to be posting another link to with more information about the EOL and so on. Another thing that's going on, Open Robotics is participating in Google Summer of Code 2022. We participate most years. We've participated last year, for example. So if you're a student and you're interested in contributing to open source, contributing to our stuff, and working with us, be sure to apply for an internship during the summer in the Northern Hemisphere. Like we announced a couple months ago, we now announce our releases, the minor releases that we do for the versions that are supported, which right now are Citadel, Edifice, and Fortress. So here are the 2 links for the release announcements that we've done since the last meeting, since the last time we met here. So if you're curious to see the latest features that are available, be sure to check those out. So without further ado, let's jump into the presentation. So I'm gonna stop sharing my screen here, and Wonsug is going to talk to us about multi-beam sonar simulation that they are doing for the DAVE project on using Gazebo Classic. So Wonsug, it's all yours. Go ahead.
Thank you, Luis. Let me start the slideshow if it pops up. Okay. All right. Thank you, Luis and Mabel. Like invited to the community talk or meetings it felt like I'm in the inner circle now. I just started the robotics community. I just joined the robotics community when I started postdoc in NPS 2 years ago, and this has been my main development for the last 2 years. And I was from acoustics, but I was not so much familiar with robotics. And now in the Gazebo Class community meeting, this is amazing. Today I want to talk about open source, physics-based, GPU parallelized, multi-beam forward-looking sonar in Gazebo Classic. I am Won-Suk Choi, a postdoc at Naval Postgraduate School, who's stationed in South Korea right now. The contents, background, and objectives, why we did this, and theory, how we did this, implementation, how we implemented, and simple validation and verifications of the results, and other usage examples and future works, related links. Starting with the background and objectives, there has been multiple previous works for the sonar simulation used in the robotics community. But the bottom line there was that it was a synthetic sonar image with the image processing which we call something similar to shading and transforming. So what they did was, here you see the pixel-wise image processing. So what they did was they project the point cloud into 2D plane, and for each pixels in the 2D image, they transformed it or shaded and colorized it into something that is similar to the sonar image. So back in 2015, it was almost like just trying to capture the shadow behind the object, because it's having a different point of view apart from the 3D point. And the 2017, Sakura made a big leap. It was called Noble GPU-based sonar simulator for the real-time application. And what they did was they pre-calculate all the acoustics, physics parameters, and databased it. And they used all those physical, they rendered, shaded the pixels with those physical acoustics parameters. But yet, as you see in this line, like color, circle color, do you see my point?
Yes, we can see.
Okay, here, this is the object, and this is a sonar, and this line is where the beams, the acoustics signals hit the ground, and because it hit here, we see this arc forming. So this is noise. This is particularly acoustics characteristics, but it does not exist in the simulation, because it's not there's nothing to image process, because there's no data in it. But we thought, and it is very important for those features to be captured, because those are the main objectives and main key parameters and main physical characteristics of underwater acoustics. And for another example, is when we are trying machine learning for the object detection, those noises should exist. And the last thing, that it dates more recent to 2019, the UV simulator, which is more like a general all-in-one packaged underwater simulation, robotic simulation, but it only had something that's similar to 2015, only shadowing characteristics. So bottom line for shortcomings of previous work was that the sonar images do not include key acoustic characteristics. We think that those are necessary. So objectives becomes, it should be physics-based. It should capture all those noises. And of course, it should be real time, because we are trying to support the underwater robotics. And to do so, we decided to adopt a it's relatively high fidelity. It's still a model, but high fidelity acoustic model that can capture key physical characteristics, such as multi-beam, because there's multiple beams, beam interference between each other, scattering noise, reflectivity, and beam directivity, and so on for each beams. So the calculations are done in beam level with actual physics inside. And to support the real-time simulation, we decided to go with NVIDIA CUDA library to use CUDA cores. And it's more like a side product of everything we did, is that because we are doing the physical calculations, we get the raw sonar data, which robotics, when they're designing their strategy, they don't have to see the final post-process or whatever colorized image, but they can actually access to somewhere more authentic signal data, which you get from all those cores if you actually connect to the actual sonar device. And the hierarchy for the development was based on the Gazebo Classic. The day project sits on top of UV Simulator, which is more like a general underwater robotics. But sadly, it stopped being maintained for like a few years back. And Project Day project has more lean toward the manipulation, but the multi-beam sonar plugin is within the Project Day to work along. So really short brief about what Project Dave is that Project Dave is an open source simulation environment to support underwater robotic solutions, especially underwater vehicles. But it's more lean toward to involve that the robotic solutions that involves autonomous manipulations. It's hosted in the GitHub repository, and if someone's interested, there's a brand new feature highlight videos you can watch. So how we did it. So this is typical multi-beam sonar diagram. I got it from the other papers. So there's a sonar attached as or bottom of the ship or in front of the ROV or underwater robots. They consist of multiple transducers, and each transducer has its own directivity pattern generated by sub transducers, meaning more like a sub transducers that vibrates in the different phases to make this beam pattern, acoustic pattern. So main lobe generates, usually main lobe generates, and if we can tilt this or whatsoever, or we can design the lobes for well, whatever purposes. And each beam, we use point scatter model for each beams. So this is the received spectrum, and this is source spectrum. And from the source spectrum, it's pretty much user definable. And from the source spectrum, the underscript J means for each beams, and underscript I means for each rays. Each ray data is calculated and summated into a single beam. Each beams are a physical thing, but each rays are more like a calculating resolution. So each beam actually exists in the physical world, and it acts actually like this beam patterns. It generates this physical shape, but rays are for the calculations for the calculation resolution. And we use this sort of model to point scatter model to calculate the spectrum of the single beams, and later that we interface and manipulate all this data to calculate the interbeam interferences and so on. And all these parameters inside, the amplitude, beam patterns, and distances, and noise, reflectivity, and incident angle, these are all physical acoustic parameters. So what we do is we calculate the spectrum for each ray and sum it into a single beam, and later we manipulate it to calculate beam interferences. And spectrum calculate, this all spectrum is calculating the frequency domain. So it's way faster. And it's more like we design the spectrum in the frequency domain and inverse FFT into time domain, which is the range data, which then can be mapped into an image to generate the sonar image. And as you see, this basic calculation equation is generated for the single beam. Each beam can be parallelized, and each ray, I parallelize GPU parallelize into calculation of each rays, and all those rays are parallel calculated and summated at the final stage to generate a single beam data set. So how we implemented it, the calculation procedure are like we get the data from the Gazebo rendering world using the generic sensor plugins. I made one that's using depth camera and one that's using GPU array. What we're trying to obtain here is basically a point cloud and angles between point of view from the sonar and the object names and so on. And when we have those parameters, we go into the standalone CUDA calculation, which is CUDA language written code. And we calculate point scatter model for each rays. We summate each rays into beams. Beam curling is calculating the interference between beams. We calculate the beam curlings, and final stage, we inverse FFT into this each vertical means number of beams, its intensity range data set, and post-process into an image. So all this is packaged into a Gazebo sensor plugin. And the final product, we cooperate with the UWLPL, Washington University. We are building a community ROS message format that involves hydrographic, hydroacoustics, data set, we work together to make a agreeable format in the community. So in details, this was what I saw in the previous videos of this community meeting. They show up some of the code, so I added this slide. So all these calculations, depth image and normal image and so on, all converted from the point cloud into OpenCV format because it's just easier to manipulate the data set, and pass it onto CUDA source code, and it has a wrapper that takes in all that variables and copy them into GPU memory and actual kernel GPU calculation kernel that performs Sonar calculation for each race. And I made it into float calculating, but because the final summation part, the float library that CUDA library support right now does not fully work with my way of doing summation. So they're not fully float calculation. It's partly like double precision and so on. But there's a possibility it can be more fast than if I know the CUDA calculation better. But it's so far half of them are double calculation and half of them are float calculation. So we tried some validation. So this was back in 2017 securities data set, as I showed before. The blue box is where the beginning of the seabed, and this is the arc where it exists in the real sonar image, but it did not in the securities. And as we see, we don't have the exact model, but we put 2 rods in the targets, and we see this arc, which is what we wanted. So key characteristics of underwater acoustics are well captured, and we went more further to get the ground truth of this plugin. And also, this was great cooperation with UWL, Laura Lindsay, and water tank, this size, target rod, we bought that rod, and Oculus, which operates in 2 different frequencies, and K-Seta, we put that right in front of the sonar camera and compared it. So first, in this model set, there's 2 different realm of parameters. One is high-level parameters, which is user-definable, such as source spectrum. This happens because all those beam patterns and source levels and so on, they're pretty much proprietary. We don't know that exactly. So there needs some calculation parameters to be calibrated before actually if you want to use one. And there are low parameters because it will be like you cannot even measure it. So it's pretty much a simplified model that's inserted into it, embedded into it. So high-level parameters are that it's a user-definable, which means you have to define it. But the sonar images are in decibel scales. They're really relative and large values. So it's to generate the image that looks realistic, it doesn't matter. But if you want to do ground truth testing, we need to calibrate it. So high-level parameters were calibrated with the source level one, that value and reflectivity and sensor gain and so on. So this was what we got. The cylinder in the sonar tank, and left was the simulation, right was the experiment, and we plotted it. And we got the rod and tank wall at the right position, and overall level was peak to noise level was well calibrated. Using this calibrated high level parameters, we changed the frequency mode to check whether the underwater physics, like underlying physics, works. With equal high level parameters used from the calibration, now it's in low frequency mode with the wider view angle because it's already deciding the machine specification. So now we get simulation and experiment. We see, same working peak noise intensity ratio. So it works for different frequencies with the same high level parameters with embedded low level calculation models. Yeah, this was a ground truth for what I did, what we developed. And here's some user examples people would love to see. Well, first of all, this is a screen capture of how it's running. So you pop it up. There's a live viewer with RTK image view. And when we change the orientations of the sonar image changes accordingly. And this is a live view, so I didn't have much of the coloring schemes. But receiving all this raw data set and post-processing with the MATLAB script, which is also included in the repository, you'll see more stunning or visually beautiful images. So that simple one road computation time benchmark was using this computer set. It was full calculation was about 0.5 hertz. If range is reduced and number of rays within the beams and the rays are reduced, it could reach up to 10 hertz. The previous screen capture GIF was almost somewhere in between this ray reduced and range reduced. And the other use case is variational reflectivity because, well, in underwater, if you're calculating this right, because we had the model, the reflectivity value is actually physical parameters. If the object is rubber or steel or mud or whatsoever, the reflectivity changes. So we tried it. The default was that this value, and when made the dimmer tank, which like rubber lining tank, or the rubber cylinder, we see different reflectivities in the sonar image. And all these are definable with object model names, thanks to Mabel Zhang, using the CSV file. And the other usage example is object degradation detection. So when object is degraded, you can capture that. And this is the shipwreck, undistorted, distorted, all those are can be captured. And this is a, well, local area search scenario. This was particularly not easy because as the title said, this is supposed to be forward-looking sonar, which object should be pretty much 2D, half semi 2D. But when we tilt it down to look down, because it grazes, there's a large it generates large range resolution, low range resolution when it's looking because it's grazing the seafloor. Always like subtle offset of all this ray resolution can make a general like large gap in the images. But I made a GPU ray based sensor can control that fidelity of how many data sets we are going to collect from the world and to make it more useful. So this is very slow so far, but it could be used because it includes all those physical aspects, characteristics behind. So when we change, let it change the view. Something's wrong with the GIF. It doesn't change anything. If you go to this link at about 150 seconds, it changes the orientation of the sonar, but refresh rate is quite slow. But this is the final product of the image. It all captured all those minor holes in the object and all the shades and so on. Future works. Well, the pretty much high priority right now is migration to ignition from Gazebo Classic, and this is pretty possible because I designed the core sonar calculation CUDA source as a standalone, like receiving all these variables and calculating its own and giving it back to Gazebo Classic source code. So migration to ignition shouldn't be so that difficult, as long as it doesn't break with the CUDA library support and so on. And there have been already a use case for similar using this plugin for the machine learning process. It actually helped to increase the accuracy of this object detection in underwater acoustics. And the other part is extended to side scan sonars, mechanical scanning sonars, and if possible, improve low-level parameters using, if you can obtain more water tank data sets. This has been published in the journal paper at the Frontiers in Robotics and AI, and this is the repository and links that relates to it. And thanks to people who have helped to make this happen. That's it. Thank you.
Well, thank you, Onsag. Does anyone have any questions for him?
Yeah, is this constrained to like freshwater, saltwater, or is this something that could be used like in the air as well? Because like I know sonar sensors are used in a variety of robotics applications.
Well, right now it doesn't have any. It does. Yeah, it can be used anywhere as long as it has those beam pattern acoustics. If you're working with those physical aspects. But you know, the radar sensors are quite different. They are really, really high frequency. They don't really well, yeah, with a little modification, because they use the same transducers, different phase, making pattern to look this way, that way. Yeah. Oh, it doesn't work right away, but it's pretty much the same background theory.
Yeah, I was also going to ask, I know CUDA is used a lot in like synthetic aperture radar and pretty heavy lift and like DSP. I didn't know if there were libraries out there that would maybe cross over a little bit between like acoustic propagation and radar signal propagation.
Right. I haven't. Well, this was my first time using the CUDA library, and I don't have much experience with all those application cases with it. But how I imagine and how I imagine from my perspective is the way they use CUDA library to parallelize is not just FFTs or just numerics, not the physics calculation back. So, well, I implemented to calculate ray-wise calculation in it. So, well, I'm not sure how those are similar or different.
I have a question about the implementation. So you said that you combined the output of a depth camera with a GPU ray sensor, or you have alternative implementations for each one of them?
Each one of them.
Okay, so you can use either one of them. Is there any advantage to using one over the other?
Well, it's more like this advantage on the depth camera sensor. The depth camera sensor only you don't have freedom how many like rays you can emit from the sonar source. Like it in the depth camera, you can decide the ratio between vertical and horizontals, and you can only define like number of vertical rays or number of horizontal rays. So the other one is like dependent. You cannot define all those. So there's one less degree of freedom of user definable parameters you can choose to obtain the data set. So I changed to GPU ray sensor. Well, it doesn't. And the other one is that because depth camera sensor is rasterized image, so the angle between so it captures into like this checkboard kind of thing. So angle between each beams are like getting larger toward when it goes toward the sideways, right? So those were not controllable. But what we want is actually full control of those space between beams, because each manufacturer has a different way of defining it and designing it. But well, the rasterization, like getting large space between them as it goes to the sideways, was more disadvantage, more unlikely to happen.
Got it. And a follow-up question is, if you weren't limited to the existing sensors in Gazebo Classic, like if you could design your own sensor from scratch, like using the rendering engine, would you create a sensor different from the GPU ray that would be better for you? That would give you data in the angles that are best for you, or?
Right, sure. Actually, I adopted the Velodyne LiDAR sensor GPU Ray version. I used that package and I wrote on top of it. So whatever they did, they worked for me. The 3D point cloud from the generic GPU Ray sensor was slightly off. I don't know. There was a discussion going on there, but the Velodyne one seems to work. So as long as I'm not doing the LiDAR, but as long as it uses GPU Ray and they did all this packagings or modification to it, so I used that one. But the main, if I were to do so, the main object will be to able to control the space between the beams.
Got it. Thank you. Any other questions? Okay, so we can go to our next presentation. Thank you again, Wunsag, and you're up, Gray. So Gray's going to be talking about ignition physics. He works with us here at Open Robotics. He's at the Singapore office, and he's going to be talking about the ignition physics library that provides an abstraction layer for interfacing with multiple physics engines inside Gazebo. So yeah, take it away.
So this presentation won't be nearly as visually interesting as the last one. It'll be very dry software engineering, but yeah, I'll do my best. So I'd like to start by talking about what is the motivation behind ignition physics? Like, why did we decide that something like ignition physics is even necessary? So one thing to, I'm sure everyone here is aware, if you've done any simulation at all, you know, different physics engines out there have different advantages and disadvantages. That's why there are so many of them, and there's like no clear winner across the board because everyone has different needs. Sometimes you care most about speed, other times you care most about accuracy. Like if you have a very complex dynamic system and you care a lot about the fine details, maybe you're fine waiting an hour for your results to come out, or maybe not. Maybe there are different types of shapes and geometries that you care about or don't care about, or different types of dynamic systems. If you care about soft or deformable surfaces, then that's going to influence what simulation is relevant to you, or fluids, or lift and drag. And some physics engines come with sort of value-added extra features like inverse kinematics and inverse dynamics, which isn't necessarily physics simulation, but just added benefits that are baked in. And many physics engines even have completely different data representations. So the two most broad, most common categories of data representations are maximal coordinates, where the physics engine considers all degrees of freedom, well, I should say all hypothetical degrees of freedom of every single body, and then deals with joints by adding constraints between bodies, versus generalized coordinates, where you kind of intentionally throw away a lot of theoretical degrees of freedom because you know certain bodies are attached in ways that don't allow the body to move in that direction. So thinking about a double pendulum, you could either have 12 degrees of freedoms and 10 constraints, or you could have just 2 degrees of freedom and don't worry about any constraints because the constraints are just baked into your equations of motion. So 2 just completely different ways of accomplishing the same physics simulation, and different physics engines will use one or the other of these most of the time. So we don't want to lock any of our users into one physics engine or into one set of features. A big objective of Gazebo and Ignition in general is we want to be an open platform. We don't want to crown a winner. We want to promote any physics engine that wants to integrate into the community. And in robotics, we target a wide user base that may have many different kinds of requirements. So like humanoid robotics care a lot about the accuracy of your simulation. If your physics are wonky, then your robot isn't going to be able to stand up no matter how good your controller is. Sometimes users care a lot about detailed contact force simulation. If you need to do some kind of grasping or interacting with your environment, then contact forces are going to be very important. If you have wonky contact forces, then well, things tend to explode, as I'm sure many of us have seen. Other times, contact forces, like contact, balance, dynamics, actually none of it matters. If you are trying to simulate like many robots in a factory, like many mobile robots, mobile robots have pretty, they're pretty well behaved as far as physics goes. You tell them where to go, they spin their wheels and they get there. And you don't really care about the slip or the drag or any of those details. So maybe you have many robots and you want a fast simulation and you don't actually care about any of the physics. Or maybe there are extra dynamics that wouldn't be covered by a rigid body simulator. Like you care about buoyancy if you have a floating or submerged vehicle, or lift and drag if you have a flying vehicle. So both of those categories are things that typically a rigid body articulated dynamics physics engine won't even touch on. And so we want to make sure that for users that do care about, or that do have this kind of robot that can fly or swim, we want them to be able to get the physics that they need. And so there's no physics engine that checks off all these boxes. And so there's no right choice for everyone. So we want Gazebo and Ignition to be a framework that allows users to have a choice about how their physics gets simulated. So to meet that motivation, we want to define an abstract layer that can be configured to support whatever combination of features a user happens to need. And part of that goal includes that there's minimal overhead and a robust API for identifying what are the features that a physics engine actually offers. Because again, different engines have different features, so we can't say this list of features is the standard that everyone must meet, no more, no less. We want to be able to say, tell us what your features are, and then users can decide whether that suits them or not. Additionally, we would like if you could program contingencies. So at runtime, figure out, does this physics engine have what I need? If not, maybe change the way I simulate things, or change what features I'm looking for, or just have some kind of way of programmatically dealing with, or maybe just like report, hey, you know what, my simulation can't run because this set of features is missing. Just report that to the user, and then let the user decide what action to take. Choose a different plugin or whatever. So as opposed to the, so in Gazebo Classic, prior to Ignition Physics, what would basically happen is if a physics engine didn't implement a feature and you try to use that feature during your simulation, you get like a printout to the console saying like that function isn't implemented for this physics engine. And by then it's too late to decide, oh, actually, maybe I should use a different physics engine. And one of my design goals is that it should not be possible for you to even try to use a physics engine feature that isn't available. So going back to the example I just gave, you shouldn't even be able to call a function that is not implemented for the physics engine that you're using. Like somehow something about the API should prevent you from even being able to call it, which probably sounds crazy at face value, but we'll explain how that can happen. And if you are the one providing the physics engine, the compiler should help you to make sure that every function you need to implement is implemented. Because it would be annoying if you know, let's say I have a nice physics engine that I want to provide to the Gazebo community, and I want to support a certain set of features, but maybe I forgot to implement one of the functions for one of those features. It would be very annoying if I ship that out and then users complain, well, this doesn't work. I'm getting this issue because, you know, some function wasn't implemented. So I, as the physics engine developer or wrapper or whatever, want to be told that, like, I want some assurance that I have done everything I need for the features that I am trying to provide. And then a final goal is we want to be able to support third-party physics engines that we don't necessarily know about ahead of time. One of the other issues with Gazebo Classic is any physics engine that you want to use in Gazebo Classic needs to be known at the time that you're compiling Gazebo. So Gazebo has support for currently up to 4 different physics engines. But if you want all 4 of them, then all 4 of them have to be available to be compiled whenever it is you're compiling all of Gazebo. So we want to avoid that and say a physics engine is a plugin. And you can compile Ignition at any time. You can compile your physics engine at any time, and they'll just work together. So some of the challenges with this, you know, whole objective is, for one thing, physics engines have a lot of different kinds of entities. By entities, I mean models, links, joints, shapes, and maybe other things. Different physics engines will actually represent these things in completely different ways. As we mentioned, there's the obvious difference between maximal and generalized coordinates, but, you know, have any 2 people try to write, try to accomplish the same software engineering task, and you will almost certainly get 2 completely different data structures written by those 2 people. Because, you know, there's just no uniform way to do absolutely everything. So we need a wrapper that can accommodate any kind of data representation that someone might want to have for all these different kinds of entities. And when you have a certain feature, which I'm intentionally keeping kind of vague about what is a feature, different features may affect the API of multiple entities in some way. So like, if you have a feature for getting the bounding box of a model, then that's typically going to require some kind of API that lets you get the bounding box of a link, which also requires some API to get the bounding box of a shape, and also requires some API to know what the transform is from your model's frame of reference to your link's frame of reference and your link to your shape. So like, this one feature touches on the APIs of at least 3 different types of entities, but you could probably add joint to that. So we can't isolate features per entity. One feature may affect the interfaces of multiple entities. And then some features may depend on the availability of other features. And this feature discovery needs to happen during runtime. As I said earlier, we want users to be able to program what should happen if a feature is missing. So like, we need to be able to discover what features are available for a plugin. So to accomplish all this, I put together this like feature system. And a feature is a class that looks like this. It defines these, oh good, you can see my cursor. It defines these inner nested classes. And each class name of these nested classes references what kind of entity it's affecting the API of. So you can include or disclude these as you wish. Like, but if your feature affects the model link and join APIs, then you'll need to include class model, class link, and class join. And inside this ... you would add whatever the API is that you want your feature to bring to that entity. So the idea is when you have a list of features, you are taking all the functions defined for these entities and you're lumping them, you will lump them all together. Or I should say Ignition Physics will lump them all together so that the model for a list of features will include all the functions of every feature included in your list of features that are put into the model entity. And then the final thing that's always required for a feature is this implementation class. So no matter which entities you are including or excluding from your feature, you always need this implementation class, which tells the whoever's writing the physics engine adapter, these are the functions you need to implement for Ignition Physics to support your feature. Okay, this is just gonna say what I was talking about. So yeah, the inner entity classes, they add something to the API of that entity, and then implementation says, here's what your physics engine needs to implement. Now, what are these templates? So the class P is for a policy. And to understand why I chose the name policy here, you can look up what policy-based design is. It's a whole C++ template metaprogramming thing that we don't really have to get into. But the policy class defines the properties that the simulation needs to have uniform across all features. So the way Ignition Physics is using this is to support different degrees of precision, like double versus float, and even different dimensionalities. So 3D simulation versus 2D simulation. Now, I think at the moment we are only using this like standard policy of double precision and 3D physics for Gazebo, or I should say for Ignition Gazebo. But in theory, Ignition Physics would be fine doing lower precision physics and even doing a 2D physics engine. And then the second class, F, is the feature list. So a feature list looks like this. You say, here are the list of joint features I need. This joint feature list inherits this is an Ignition Physics feature list. I left out the namespace here, but this feature list template comes with Ignition Physics. And then you just state like the entire list of features that you care about including in this feature list. And so this is the object that will end up being passed into here. And then how can I have features that depend on other features? Because I said that's something that's needed sometimes. So when you define your feature, so this add link external force torque, this is a feature just like the my feature that I mentioned earlier. What you do is you have this inherit the feature with requirements template, and then you give it a feature list of whatever features your feature depends on. And when you do that, this like add external force function that you want to have in your link class for your feature, this function can now use any functions that are defined in the link frame semantics. So whatever features are in your required feature list, you can now use in the functions of the feature that you're defining. So it goes beyond just saying, please always make sure this feature is available, but it actually guarantees that you can use that feature within your feature. And yeah, so add external force, it requires frame semantics so that it can figure out, well, how do I calculate the effect of this relative force? Like, how do I know what direction this relative force is pushing in and what the position is, because these inputs are, they're designed to be relative, so they need to know the frame semantics to be useful. And ignition physics will automatically make sure that this link frame semantics feature is included or like pulled into any feature list that includes add link external force torque. It'll do that automatically. Now, if you want to implement a physics engine wrapper, then you need to define a class that inherits the ignition physics implements 3D feature list. So this 3D could be swapped out for 2D, 3F, 2F, for whichever policy you want to use. But again, so far we're only using 3D. So if you want to make my physics wrapper, you'll inherit virtual implements 3D my feature list. And then in this class, you need to provide an implementation for every function that is defined in the nested implementation classes of every feature in my feature list. And if you neglect one of those functions, the compiler will give you an error, a compilation error, saying, hey, you're missing this abstract function. You're missing an implementation for this virtual function, so we cannot create your physics engine wrapper. Yeah, so it's, I know no one likes compilation errors, like no one enjoys receiving them, but it's, better to know earlier rather than later, better to know like before you ship something out than when people come up later complaining that your physics engine isn't working for them. So to actually use a physics engine, here's the process. Ignition physics depends a lot on ignition plugin for the whole plugin system. Like we said, the physics engine is a plugin now. So the first thing we have to do is make a loader. So you make your plugin loader and you load lib, find your SO however you need to, but for now, let's just pretend we have it right next to us in my physicsengine.so. And once you've loaded your library, you instantiate whatever physics engine plugin name you want from that library. So these are things that you kind of, well, okay, so you need to come up with some strategy for finding the library. I mean, Ignition Gazebo has its own strategy for loading plugins. So if you're using Ignition Physics directly, then you need a strategy for this. As in terms of knowing which plugin to instantiate, Ignition plugin actually has plugin discovery. So you can get a list of the names of all the plugins that are supported, and you can even look at what interfaces they provide. So anyway, there are built-in ways to do plugin discovery, but for now we can pretend that we just know the name of the plugin we care about. So after you've loaded that plugin, you now switch over to Ignition Physics and you use the request engine function to try to get an engine out of this plugin that matches whatever your feature list is that you care about. So you say request engine with this feature list from this plugin. And the next thing you need to do is check, did I get a valid engine? The engine itself will be, it's not technically null pointer, but it's a thing very similar to null pointer. So it's a thing where you can check, like, is this valid by saying, if this or if not this. And so if you get back an invalid object, then you just say like, oh no, features are missing, or you handle it a different way. Maybe instead you say request engine 3D again, but with a different feature list. And you just tell your user, hey, we're gonna ignore certain features this time. Or you can try instantiating a different plugin, or whatever you want to do. It's totally up to you, because you can program this stuff however you want. But if your physics engine is valid, then you can start using it. For example, if your feature list included construct empty world, then you can now say engine drill construct empty world, my world. And if it also included the feature construct empty model, then you can call this. If you try to call a function that was not one of the features in your feature list, you get a compilation error. So if, suppose your feature list did not include the feature for constructing an empty model, then this line right here would end up just being a compilation error saying the compiler couldn't find that function for that class. So any functions you want to use must have been, or any functions that the compiler lets you use must have been in your feature list. And if your entities are valid, then it must have that feature. These are all things that are like guaranteed by the compiler and by the wrappers of Ignition plugin and Ignition physics. So now I'll talk a little bit about some of the intentions versus some of the realities. So Ignition physics was, like when I originally designed it, it was actually before the Ignition Gazebo ECS existed. And so what I had in mind was that if you are writing a plugin for like a model or a sensor, you would actually have access to the Ignition physics API itself. And then your model plugin could actually inspect what features are available in the current physics plugin, and do those features fit the needs of my model or of my like model plugin or sensor plugin. And if they do, then okay, proceed as normal. If not, then do a fallback behavior, or I don't know, like throw an exception, or you have to decide how you want your plugin to handle that. But whatever the case, you would at least know within your plugin that some requirement isn't being met. The current reality is that Ignition Gazebo ECS is sitting in the middle. So Ignition physics is actually being used by only the physics system of Ignition Gazebo. So only that system has the benefits of the API, of the Ignition physics API.
Great, just a quick heads up that we have like 2 minutes left only.
Okay, yeah, this is my last slide. So also Ignition physics was meant to be extremely lightweight, which is true in terms of like runtime performance, but right now the binaries that it generates are very big because of all the template craziness. So yeah, and then I mentioned earlier, it can target 2D and 3D, but I don't think anyone has a 2D engine wrapper yet. So now in terms of addressing some of these realities, maybe Ignition Gazebo can have a registry that could give access to Ignition physics, if that's something that's desirable. If not, then that's fine, forget about it. For the like crazy template giant binaries, one way I think that could actually be fixed is to eliminate the dependency resolution and deduplication. So when I said when you have required features, it'll pull those features in automatically, that like making that work was very complex. Like it involved a lot of very complex templates that are in a large way responsible for the giant binary blobs that are being generated. So we could actually just throw that feature of Ignition physics away. It'll hurt usability a little bit, but it'll probably really improve binary sizes and compile times. And as far as getting a 2D engine, you know, applications are welcome, or contributions are welcome if anyone has any interest in doing that. Ignition Physics is like ready to go for that, so could be done in theory. Okay, I guess we're out of time, but I'll be happy to take any questions if anyone wants to stick around.
Yeah, thank you, Gray. I think we can do at least one question. That was very nice, very, very in-depth discussion about ignition physics. Are there any questions? And I think we can wrap up. Oh, go, Steve.
Yeah, so given what you know now about the Ignition Gazebo ECS, how would you design Ignition Physics differently, or would you have suggested that Ignition Gazebo be designed differently? What are your thoughts?
That's really tough. I guess, I mean, one option would be to put some of this like feature, I don't know, like feature discovery concept into Ignition Gazebo directly, into the ECS directly. That might be the way to go. I mean, I think conceptually Ignition Physics is pretty cool, but I think the reality is no one's actually using it outside of Ignition Gazebo. And so it creates some redundancy. But at the same time, I personally feel that there are benefits to some of the features. Like one of the things that's very tricky with ECS, like implementing an ECS system, is making sure that you are consuming and producing all the components that you need to. Because ECS is by design very loosey-goosey. So it doesn't ensure that your system is meeting all of its responsibilities. Whereas the Ignition Physics by design creates this it's flexible in the sense that you can choose what features you're dealing with, but at the same time it's rigid in that whatever features you claim to be providing or using must be there. So you know, you get to declare what features you want, and then the whole like compiler template system guarantees that you're implementing all the things you need to implement. So I can imagine without Ignition Physics, we'd probably have challenges where every time we try to incorporate a new physics engine, maybe there's like this ramp up period where we keep realizing, oh, like we're forgetting to publish this component or that component, or forgetting to take in these components, like these commands, or you know, this or that, and we don't find out about that until a user eventually tries to do that thing and complains that it's not working for that physics engine. So yeah, I'm not sure. I'm not sure if I would do things differently, except maybe get rid of the dependency system. I think that was very well intentioned, but yeah, it's probably not worth it. Just because of the crazy size of the binary blobs and compilation times. Like I think that can just be way, way better than it is right now.
Thanks.
Thank you, Gray. So I think we're gonna wrap up here. Thank you again, Woonsug and Gray, for the presentations. That was very nice. So like, we don't have time to go over the news, but if people want to check out the links that Kat curated for us, go to the agenda, and I'll see everybody next month. And this is going to be recorded and it's going to be on YouTube as well. So see you all. Bye-bye.
Thanks, everyone.
Thank you.